My name is Bhairav Mehta, and I'm a PhD student at MIT. And today I'll be presenting a user's guide to calibrating robotic simulators, a CoRL 2020 paper that I was lucky to work on with Ankur Handa, Dieter Fox, and Fabio Ramos at NVIDIA Research in Seattle. Simulators are a critical component of modern robotics research. For both perception and decision-making can be studied in simulation before being deployed to real-world systems, saving on time and costs from both a financial perspective, but also from a safety perspective. Simulators have made great strides in the past few years, and as a result, we see a lot of academic work and industry work starting in simulation. What we see here is a popular Majoko simulator on the left-hand side, as well as the more recent Omniverse simulator that's developed by NVIDIA on the right-hand side. However, issues with this paradigm still persist, especially when we're doing learning directly in simulators. The well-known reality gap requires techniques to correctly estimate a multitude of parameters, many of which aren't even known on the real robot. What we see on the slides is a table from a recent paper that describes all the different parameters in the simulator that have to actually be calibrated before work can continue. Despite the significant progress in research of sim-to-real algorithms or things like domain randomization, the analysis of different methods is still conducted in an ad hoc manner without a consistent set of tests and metrics for comparison. There is recent growing interest in the robot learning community in the field of what we call calibrated simulation and adaptive learning. A lot of this can be categorized as machine learning for system identification. This line of work, which merges the machine learning and system identification communities, is able to incorporate real-world trajectory data into the calibration or policy learning process. Real-world data can allow for better environment sampling within simulators, more accurate uncertainty estimates for environment parameters, and more robust policy learning. What we see in this slide is a general paradigm for calibrating robotic simulators. We first set up the task on the target environment, which is usually the real-world robot. We then collect demonstrations from an expert or a human in the target environment. We train a parameter estimator to estimate parameters from those trajectories, and then we calibrate our simulator in the final step using those estimated parameters. Calibrating and adaptive simulations hold really great promise for robot learning, as a correct set of simulation parameters can help bridge the sim-to-real gap in a wide range of challenging tasks. In this work, we explore failure modes of each algorithm in this space and present a user's guide on when and where to use each. To present our results cleanly, we introduce the Simulation Parameter Estimation Benchmark, also known as SIPI, which provides tools to efficiently test and compare past, current, and future algorithms in this space. The SIPI benchmark, which we'll release with code at CoRL, comes with environments, calibrated randomizations, training, testing, and validation data from all environments, an easy-to-use API, as well as clean and auto-generated plots to compare. Here's a quick code sample showing that with an implementation of a parameter estimator, many of which ship with our library, calibration can be done in less than around 10 lines of code. Our paper is not only introducing a new benchmark, but we also overview a wide class of algorithms on a variety of tasks, some of which are seen here. While our full results can be found in the PDF, we highlight the most interesting in this video. Meta-learning approaches seem to do extremely well in lower dimensional calibration settings, whereas particle-based approaches like active domain randomization and SimOpt do better in high-dimensional parameter settings, but with larger spread. We explain our hyperparameter search in depth in our paper and provide validation data for every environment so that these results are more used as a starting reference point rather than a de facto statement of which estimators perform the best. Another popular experiment that we use is calibrated domain randomization. We calibrate simulators with training data from some environments, and then we use those estimated parameter settings to train new policies and track task performance. This allows for better, more agnostic comparison of algorithms such as MAML, which generate point estimates of parameter settings, ADR and SimOp, which are particle-based, and even BaseSim, an estimation algorithm that incorporates uncertainty by estimating a posterior over the parameters. While we find generally that distributions of training environments help improve robustness and performance of policies, we hope these results spawn new and future approaches to improve parameter estimation. Thank you for your time, and you can check out our code on GitHub at this link here. Thank you.